Hello guys and welcome to another calculus video. In this video we are going to be taking on this awesome integral that you can see right here. I got this from a big list of integrals, which I think is super cool, so maybe I'll post that in the description. And yeah, so it's a pretty fun problem, so let's go ahead and jump right into it. We are going to be using a lot of lemmas for this one, but that's a great thing about learning math is that whenever you derive a formula or something, you always end up coming back and using it again. So you can always build off of your past work. So here are a lot of things that I've proved in previous videos, starting off with this contour integration formula. The integral from 0 to infinity of sine ax over hyperbolic sine of x dx equals pi over 2 tan h pi a over 2. And then another really cool one is the Laplace transform of hyperbolic tangent of t, which is this expression with digamma functions. Then these are some more trivial identities right here with Laplace transforms of sine xt and tf of t. And finally, we have two specific values of the trigamma function, which also another separate video that I made in the past. I'll go ahead and link all of these videos as cards in the top right corner. May take a bit for all of them to pop up though. So let's go ahead and jump right into the integration. So we start with this problem, and really the key here is to notice a few of funky things about this hyperbolic cosecant, which is essentially just a hyperbolic sign in the bottom, and so it would be really nice if we were able to get a sign of x out there somewhere, and that's exactly what we're going to do. So we're going to redefine this using some function I of s, and obviously here when s equals 1 we get back our original function. When s equals 0 we just get 0, of course. So let's go ahead and take a look at how this is going to at how we're going to solve this. So basically, the first thing we're going to do is we're going to take the inverse Laplace transform of our function I of s. And already we're jumping into some weird stuff, but essentially we're going to use the fact that the inverse Laplace transform of the integral of a function of x and s dx is the same as the integral of the Laplace transform dx. Now obviously this is contingent on a few conditions. Obviously the function can't be wildly oscillating and it has to have subpolynomial growth, but essentially we can do this using Fubini's theorem because the inverse Laplace transform is also defined as an integral. So that means we can go ahead and not worry about this hyperbolic cosecant, and we can bring the inverse Laplace transform in here. And this means we have to find now the inverse Laplace transform of sx over s squared plus x squared squared. And notice that this expression right here is actually just negative 1/2 times the derivative of x over s squared plus x squared. Then, using our rules for Laplace transforms, we know that we can actually replace this with t times sine of xt. And this gives us our inverse Laplace transform of our function I. So this is a sort of an I of t in comparison to our original I of s, and we'll take the forward Laplace transform later. But anyway, once we reorganize and factor out this t, we get this expression right here, which is very easy to transform into the formula that we had earlier. So once we go ahead and substitute pi x over 2 to be u, we get 1 over pi times t times the integral from 0 to infinity of sine of 2u t over pi over sine hu. Then again, just plug in that formula that we have from earlier. In this case, our a value is 2t over pi. And so we're overall going to get the inverse Laplace transform of I being t over 2 times hyperbolic tangent of t. So now we just have to go ahead and take the forward Laplace transform. And that will recover our original function I of s, which is one of the great things about Laplace transform is that it's 1-to-1, so you can take inverses and forwards and repeat that process as long as you want. So we get I of s equals negative 1/2 d over ds, Laplace transform of hyperbolic tangent of t, just using the rule for this t in front. And so we go ahead and substitute in the Laplace transform of hyperbolic tangent of t, which I have from earlier, right here. And then we go ahead and differentiate it, and we get some expression with the trigamma function. And now all we have to do is go ahead and plug in our value of s, which is going to be 1, because as we discussed earlier, I of 1 is just I. And this is going to be 1/16 times trigamma 1/4 minus trigamma 3/4, all minus 1/2. We go ahead and substitute in the derived values for this. And actually, it's easier to go ahead and write out what trigamma 1/4 and trigamma 3/4 are. I'll go ahead and demonstrate this off to the side here. Since because of the way that the trigamma function is defined, we have that trigamma of x equals the sum of 1 over n plus x squared from 0 to infinity. So this means that our trigamma of 1/4 minus trigamma of 3/4, once we go ahead and shift the indices in both these summations, we get the sum from 0 to infinity of 1 over n plus 1/4 squared minus 1 over n plus 3/4 squared, which is the same as 16 times the sum from 0 to infinity of 1 over 4n plus 1 squared minus 1 over 4n plus 3 squared. And notice that we're just taking all the odd numbers and we're splitting them up into odd numbers that are mod 1, are 1 mod 4 and 3 mod 4. So that's actually going to give us 16 times the sum from 0 to infinity of negative 1 to the n, since we're alternating all of those odd numbers over 2n plus 1 squared. And this is just g. So that gives us our result right here, which I just went ahead here and plugged in the actual values. So we go ahead and we get 16g in here. And so then we end up just getting g minus 1/2 for our final result for this absolutely marvelous integral. So I hope you guys enjoyed this short little problem. It wasn't a lot of work, but we did rely on a lot of lemmas. But again, as I said, I just really enjoy when you get to work on a problem and you get to notice, oh, I used this in this other problem, or I derived this formula, you know, almost a year, almost like, I don't know, 8 months ago for some of these. So yeah, it's really exciting to be able to use all those formulas that I worked hard to derive. So I hope you guys enjoyed the video, and I'll see you next time.